Welcome everyone. Myself Vijay and my teammate Advait are presenting a brief overview of quantum safe algorithms, the hard problems behind them, and the attacks on such algorithms. So we are going to cover what is quantum computing, Shor's algorithm that broke the discrete logarithm and the factorization problems, how new algorithms are deemed quantum resistant, and we would look into hash-based signatures and lattice-based key encapsulation schemes. So we would also discuss the future works. So what is quantum computing? So I would like to start with giving a brief introduction about it. So it is a field of computing that utilizes the principles of quantum mechanics. So unlike classical computers, which use bits, the quantum computers use quantum bits or qubits. Qubits can represent multiple states simultaneously, allowing for complex computations. It has the potential to solve problems much faster than classical computation. So how does quantum computing achieve a very high speed up? So here is the trick. A quantum computer can handle multiple classical states simultaneously. So this is called a superposition. A classical state can be 0 or 1. However, a quantum superposition can be a linear combination of both. Also, in quantum, the resultants are amplitudes. Hence, it does not act like probabilities in classical states. Unlike probabilities, there is a possibility that opposing amplitudes can cancel out during quantum interference. This is unlike classical setup, where the probabilities for different possibilities always sum up to 1. So let's look at Shor's algorithm and how it became a big threat to the previous cryptographic schemes in the post-quantum era. So when there is a clever way of arranging the different classical states in such a way that the right answers add up and the wrong answers cancel out by interference, then there is a big time gain. So the Shor's algorithm uses the property mentioned above to turn a bad guess into a good guess, which might share a factor with n when trying to find the factors of n. So this step was the bottleneck in classical setting. Now it can be solved in quantum within seconds. So using quantum interference, in case we choose all the possible elements with a remainder 3 in this case, for all the other elements, the amplitudes tend to cancel out during quantum interference. So hence we are only left behind with the elements that have a remainder of 3. So to solve this, we use another property called quantum Fourier transform, and this is also called period finding. And after finding this period, the inverse of this period gives the better guess. So the Shor's algorithm has actually broken the factorization problem, and it can also be modified to solve the discrete logarithm problem in the quantum setting. Hence, we need to look at better schemes for the post-quantum world. Now let's move on to hash-based signatures. Hash-based signatures are considered a compelling option for ensuring digital signature security in the post-quantum era. We are assuming the following concepts are known: the Lampert's one-time signature scheme, Winternit's one-time signature scheme, the gold stateless hash-based signatures, and hash functions like SHA-2. The Lampert's and the Winternit schemes had very long public keys. Hence, Merkle created a binary tree from the hashes of private keys as leaf nodes. The parent is constructed by the combined hash of the children at each level. Finally, we reach the root node, which is the public key that is shared. It is a stateful scheme where the counter or the list of keys used needs to be maintained. It can sign n messages where n is the number of leaf nodes. Hypertrees are Merkle trees constructed over Merkle trees, where a leaf of the upper tree signs the root of the lower tree. By choosing the height of each subtree, we can find a balance between performance, that is the number of expanded nodes, and the size of the signature. Horse, which is the short for hash obtained on random subset, it is a few times signature scheme where the same key set can be used for signing a few messages till a threshold is reached where enough of the secret has been compromised. It is unlike the Winternit's or Lamport scheme where keys can be used for signing just a single message. A high length random array of private keys is generated and they are hashed to generate public keys. Horse effectively splits the messages into blocks and uses the hash of each chunk as the index to get the signature of that particular chunk. Hence, based on the key space size, the probability of finding a collision is computed and is found to be very small when the key space is very high. However, there are two disadvantages. The size of the public key is very large. And also, if the same chunk is repeated, the signature is going to repeat as well, and hence there is a possibility of forgery. To avoid the disadvantage of having a big public key, horse is converted to Horst, which is a horse with a hypertree. And hence the public key now has a length of a single hash output. In force, a different Merkle tree for each index of the chunk is created so that there is no overlapping path and the problem of repeating chunk with horse is solved. Sphinx plus is one of the post-quantum safe cryptographic algorithms. It involves a hypertree construction where the hypertrees use Winternit's one-time signature system to add many trees, and the last node uses a Winternit's one-time signature system to solve the force key for the message. Sphinx Plus is a hash-based algorithm, and the hard problem in Sphinx Plus is the collision resistance of the hash function that has been used. For the hash function, we have considered SHA-256, which is used by Sphinx Plus. The generic attack is using the vulnerability of horse or force, where after a series of messages, a major portion of the secret will be compromised and hence it is deemed unsafe. So that particular threshold is called gamma. Here you can find the status of classical attacks on a reduced SHA-2 algorithm. In this setting is called semi-free star collision, and in this setting, the attacker tries to find a different message which tries to output the same hash, given that the initialization vectors are different. This is not a real collision attack because the initialization vectors have to be same, and then only you can create a real forgery. So this is an image showing how a single semi-free collision is converted into a two-block collision. So to convert it, for the conversion to happen, you need to have at least 2x semi-free star collisions. In a classical setting, the value of x essentially needs to be at least n by 2. So at 38 steps, the number of semi-free collisions is not sufficient. But in a quantum setting, using Grover's algorithm, the complexity can be reduced to the root of the original. So there is a very small constraint on x. And hence, it is possible to convert a semi-free collision at 38 steps to a two-block collision when there is a quantum setup. This slide includes all the points that we mentioned in the previous slide. Moving to lattice-based encryption schemes. Lattice-based encryption schemes are a class of cryptographic systems that rely on the hardness of certain mathematical problems associated with lattices for their security. The concepts mentioned below are just skimmed through due to lack of time during the presentation. In cryptography, lattice is a mathematical structure consisting of evenly spaced grid points in an n-dimensional space. Lattices are defined by two key components, bases and points. A set of linearly independent vectors, often denoted as b1 up to bn, is called the basis. The lattice is generated using a linear combination of the bases. Our Cartesian system 2D grid can be considered as a simple lattice. The unit vector in the x direction and the unit vector in the y direction are the basis vectors. All the points in the lattice can be generated as a linear combination of these two basis vectors. A good basis is where the basis vectors are close to orthogonal and are of comparable lengths. For example, the unit x and the unit y vectors in 2D Cartesian lattice are good bases. A bad basis negates the above conditions. The shortest vector problem is to find the shortest vector in the lattice, which is essentially finding the closest vector to the origin. The closest vector problem is to find the closest vector to a given n-dimensional vector, which does not need to be a point in the lattice. The equations on the right show a system of linear equations that are overdetermined, and there are ways to achieve a solution in polynomial time. This represents learning without errors. However, if a noise is added to the bias term, then it becomes a hard problem. This is called learning with errors. Crystal Kyber uses module LWE, which is more secure than a ring LWE. The public keys are matrix A and T, and the private keys are the basis S and the error E. This is the public key encryption scheme used by Crystal Kyber. It is combined with Fujisaki-Okamoto transform to generate a key encapsulation scheme, and hence it removes the vulnerability of being a public encryption scheme. LLL is a reduction technique that is used to get simple good basis from a complex bad basis. As you can see, the Gram-Schmidt coefficient being less than 0.5 means that the jth Gram-Schmidt vector must be nearly orthogonal to the basis vector. Also, the lowest condition ensures that the reduction on each step does not exceed a limit, like the reduction factor is 1/4 when mu is 0.5. After each step, the basis becomes more orthogonal and smaller, thus making the hard problem easier. The BKZ uses a polynomial time oracle for solving SVP in a smaller dimension and iteratively uses LLL for basis reduction. In the enumeration technique, the larger vector is projected orthogonally on the hyperplane of the smaller vector. Then a grid is made parallel to the smaller vector and spaced by the length of the projection. The points that are within the sphere of the radius of the smaller vector are considered. Then the search space is reduced, as these are the only candidates that are chosen. In this, the search space can be even pruned. The sievings process starts by finding many vectors that have lengths comparable to the basis vectors, using the linear combinations of the basis vectors. The difference between the closest vectors should be essentially short, and hence we tend to reduce and converge towards the SVP in multiple iterations. After multiple iterations, we reach the solution, and there are problems like landing a collision and exponential running time, which needs to be solved. So we come to the most important attack that we found, which is an MLP model that is used to perform supervised learning on predicting the plain text message based on power consumption during the decapsulation process in Kyber. The CPA PKE functions, which is the public key encryption functions, are available. Hence, a training set was created for a set of input messages for a single public-private key pair. The power consumption traces were recorded for the different plaintext and a label dataset was created. However, this message is chosen and is specific to a specific hardware it is trained on. Following are the other side channel attacks on Crystal Kyber. To conclude, we would like to extend our future plan, and we would like to investigate code-based and multivariate quadratic-based cryptographic algorithms in the future. Thank you for listening.